So in this video, what we want to do is derive the sum and difference identities for the cosine function. But before we do that, let's take a look at the sum and difference identities. They're called the sum and difference identities because they involve taking the cosine of either a difference or a sum of two angles. And what we identify is that if we want to know the cosine of the difference between alpha and beta, we can take the product of the cosine of alpha and beta and add to it the product of the sine of alpha and beta. And if we want to find the cosine of the sum of two angles, we just take the product of the cosines of the two angles and we subtract the product of the sine of the two angles. And the type of geometry where this turns up and is useful, so I just wanted to give an example of when this has some utility. You might have a situation like this where you have two right triangles. So a smaller right triangle, a larger right triangle, where the angles alpha and beta are measurable, and because alpha and beta are both associated with right triangles, we are able to use right angle trigonometry and our definitions for cosine and sine to be able to figure out anything we want to know about the cosine and sine of alpha and beta. But notice that the angle between them, that's the angle that's formed by the hypotenuse of the two right triangles, so I'll call that phi. This triangle isn't a right triangle, so I can't get at the cosine or sine of phi by using right triangle trigonometry. But we notice that the cosine of phi, that phi is just the difference between alpha and beta. So if I wanted to know the cosine of phi, I could use identity number 1 to calculate that cosine, because I can find the cosine and sine of alpha and beta, both of which are based on right triangles. So to get at the derivation for the cosine of the difference between two angles, we're going to start by constructing a triangle in quadrant 1. And this guy here is associated with a right triangle. And I'm going to call the angle in standard form right here. I'm going to call him alpha. And then I'm going to recognize that there's another right triangle in this picture right here. That's a horrible right triangle symbol. So in this angle right here, I'm going to call it beta. And then I want to notice that the angle here is, which I'll call phi, I want to notice that phi is alpha minus beta. So once I establish those angles, alpha and beta, the next thing I want to do is remember what I know about the unit circle. So on the unit circle, what we've already determined is that if you have any point xy on the unit circle, that if you know the angle theta in standard form, for which xy forms the terminal side, then we know that this ordered pair xy can be described as the cosine of theta, comma, the sine of theta, where theta is that angle in standard form. So this point right here is going to have coordinates cosine of alpha, sine of alpha. And this point right here will have coordinates that are given by cosine of beta, sine of beta. And then we want to notice that we can construct a right triangle right here using those 2 points. And the width of this right triangle is just going to be the absolute value of the difference between the two x coordinates, so cosine alpha minus cosine beta. And the height of this right triangle is just going to be the absolute value of the difference between the y coordinates, sine alpha minus sine beta. And the line segment connecting the 2 points is just the hypotenuse of the right triangle right here. So I'm going to say, hey, this is length d. So that tells us that we can use the Pythagorean theorem, which says that the hypotenuse squared, or d squared, is just equal to the sum of the squares of the legs of the right triangle. So it's going to be cosine alpha minus cosine beta, the difference between the x coordinates. And this is going to be sine of alpha minus sine of beta, the difference between the y coordinates, to get the height of that right triangle. And then I can simplify d squared a little bit by expanding this. So take cosine alpha minus cosine beta and square it, which will give us cosine squared of alpha, because we'll have a cosine times cosine, and then we're going to get minus a cosine alpha times cosine of beta 2 times. We get the middle term twice. So we'll have 2 cosine alphas cosine betas if we were to multiply that all out. And we would get a minus cosine beta times minus cosine beta would be a plus cosine of beta squared. Plus, then we could square this out, which would give us sine alpha times sine alpha is sine alpha squared, minus sine alpha times beta 2 times. We get the middle terms twice, so minus 2 times sine alpha sine beta, and we get minus sine beta times minus sine beta is plus sine squared of beta. And then we want to remember the Pythagorean identity that says the cosine squared of any angle plus the sine squared of any angle has to equal 1. So here I see I have cosine squared of alpha plus cos plus sine squared of alpha. So this actually just equals 1 by the Pythagorean identity. And here I see I have a cosine squared of beta plus sine squared of beta, which just equals 1 by the Pythagorean identity. So I'm going to get 1 plus 1 is 2 minus 2 cosines of alpha cosine beta minus 2 sine alpha sine beta. And that's the square of the distance between those 2 points on this triangle. And we want to hang on to this because we're going to use it in a couple slides. And then our next move is going to be to take this right triangle, not the right triangle, this triangle that we constructed right here, and we're going to rotate it through an angle of minus b degrees or b radians, however we're measuring this angle. We're going to rotate it so that the triangle lays down on the positive x-axis. So on the next slide I've done that. I've rotated it this way. So this angle here is still the same angle phi that it was in the previous image, but phi was just the difference between alpha and beta. So we want to recognize this is phi equals alpha minus beta is this angle. And again, this is an angle now in standard form. So I know the coordinates right here are cosine phi sine phi, or cosine alpha minus beta, comma sine alpha minus beta. And here I have the ordered pair 1, 0. And this distance d is the same distance it was before we rotated the triangle. Rotating isn't going to change distances. Rotation is an isometry, or a distance preserving transformation of the plane. So we can use the Pythagorean theorem again to find out what d squared is. And d squared is just going to be the square of the difference between the x coordinates. So cosine alpha minus beta minus 1 plus the difference between the y coordinates, which is going to turn out to be just sine of alpha minus beta because we're subtracting a 0, So the height of our right triangle is just the sine of alpha minus beta. So we're going to square that. And just like before, we're going to square this out and simplify a little bit. So I'm going to get cosine of alpha minus beta times itself, so it'll be squared, minus 1 times the cosine of alpha minus beta will happen 2 times, so we'll get 2 cosine alpha minus beta. We always get the middle term twice when we square something. And we get minus 1 times minus 1 is a plus 1. And then we're still plus a sine squared of alpha minus beta. And then we want to recognize that the Pythagorean identity is showing up. It says, hey, the cosine squared of an angle, which alpha minus beta is just some angle, plus the sine squared of the same angle is, by the Pythagorean identity, just equal to 1. So we get 1 plus 1 is 2 minus 2 cosine of alpha minus beta. So what we've done is find 2 ways to describe the square of this distance. So if we grab both of those ways of describing the square of the distance, the transitive property of equality says that if this is equal to d squared and this is equal to d squared, then these 2 things are equal to each other. So 2 minus 2 cosine of alpha minus beta, because it's equal to d squared, is also going to be equal to 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. We could actually subtract 2 from both sides, which would kill this. And then we could divide both sides by negative 2 to get the cosine of alpha minus beta by itself. So divide everything on both sides by negative 2, which is going to leave us with cosine of alpha minus beta equaling negative 2 divided by negative 2 is 1. So we just get 1 cosine alpha cosine beta, minus divided by minus is a plusy, and the 2's are going to become a 1, so we're just going to get a sine alpha sine beta. And there's the difference identity for the cosine function that says the cosine of the difference between alpha and beta is the same as this other stuff. They look different, but they mean the same thing. To get the identity for the sum of alpha and beta, all we need to do is recognize that alpha and beta are arbitrary angles. We can let them equal anything that we want. Alpha can be 50 degrees, beta can be 2,000 degrees. It doesn't matter. They're arbitrary angles. So what we can do is let B be the angle negative beta, or the opposite of beta, and then make that substitution. So we'll go cosine of alpha minus, hey, we can put any angle in for beta that we want. I'm going to put the opposite of beta in for it, equals the cosine of alpha times the cosine of, we replaced beta in the formula with the opposite of beta. So everywhere I see a beta in the original identity, I'm going to replace that beta with, that beta gets replaced with the opposite of beta. And then we can simplify a little bit here. We have a double negation, so this is going to give us the cosine of the sum, alpha plus beta. And then here, cosine alpha is going to stay the same. Here we can use a symmetry identity. So we already learned that the cosine function has even symmetry, so the cosine of the opposite of beta is the same as the cosine of beta by the even symmetry of the cosine function. So we can replace the cosine of the opposite of beta with the cosine of beta, and then I'm going to get a plus. I'm going to get sine alpha, but sine of the opposite of beta. Well, we've already discovered previously that the sine function has odd symmetry. So what we discovered was that the sine of the opposite of beta had to equal the opposite of the sine of beta. by odd symmetry. So we can replace the sine of opposite of beta with the opposite of the sine of beta. So right here I can replace this with the opposite of the sine of beta, but this negation can come out here combined with this addition, so we get a positive times a negative is a negative or a subtraction, and we wind up just getting the sine of beta here, which establishes the second identity we needed to establish. So that's where the two identities, sum and difference identities for the cosine function come from. That's one way to derive them. There are other ways. I happen to like this one.